My name is Jorge Novillo. I'm a technical enablement PM on the strategy and ecosystem team at Microsoft. Windows fundamentals in battery life is where I love to focus all my time and energy. I'm very excited and grateful to be here with you today to review our latest battery life optimization story and walk through several demos that will give you an idea of the types of exercises that we'll be covering at the WinHEC Battery Life Lab. Doesn't matter if you're in business development, engineering, marketing, I think we could all agree that customers consider battery life to be a feature. If you look at user reviews of Windows devices from Microsoft Store, you may notice that there's a direct correlation between great fundamentals and high customer satisfaction. The first review here reads, absolutely love this computer, beautiful laptop, nice 1080p touchscreen, and great battery life. The second review says, I've had this laptop for just a month, love the battery life, I can use it for several hours a day for 3 or 4 days without charging it. Our goal at Microsoft is to partner with you to ship innovative Windows devices that deliver long and consistent battery life and earn positive reviews like these. So we have 4 main areas that we're going to focus on in this talk today. We'll start by reviewing battery life features in Windows. This includes the performance power slider, the energy estimation engine, and the battery user experiences, to name a few. Then we'll switch gears and share some updates on battery life assessments, which can be used to assess your devices before you ship and make sure you're on track as far as meeting your battery life goals. Next, we'll review the benefits of hardware-based power measurement solutions. So by integrating power meters into your pre-production devices and leveraging the dev kits that your silicon vendors offer, you can improve your BOM selection process and scale out your energy efficiency optimization efforts within your organization. We'll end by reviewing optimization tools such as the Windows Performance Analyzer and Media Experience Analyzer. These tools are used to identify opportunities to improve energy efficiency of your OEM preload. Before we get started, let's briefly review some hardware design aspects of shipping devices with long battery life. Building Windows devices that deliver long battery life starts with selecting energy efficient hardware components and making smart design trade-offs. Our amazing and innovative OEM and ODM partners are experts at identifying customer expectations for each form factor and price point and designing devices that strike the right balance between size, weight, cost, functionality, performance, and last but not least, power. We encourage our partners to take advantage of power-saving features in Windows. For example, you've probably heard me say in the past, make sure that you consider using audio offload, which can save anywhere between 4 and 14% battery life. Also, low refresh rate panels. Low refresh rate panels can save anywhere between 3 and 5% during full screen video playback. Jumping from a full HD to a higher resolution panel, such as 4K, can also increase the power consumption by up to 20%. So there's some design considerations and design trade-offs. You guys are the experts at this. Just wanted to make sure that you were aware that you guys are at the foundation, right? The OS sits on top of everything, all the hardware and firmware that you develop, and you guys are the experts at this. So with these design trade-offs in mind, it is essential that we define clear battery life goals and detailed power models prior to locking down our BOM. In addition to looking up the power stats and data sheets, we recommend that you use the Silicon Partners reference designs and dev kits to confirm that all the components you choose for your devices actually meet those specs that are defined in the data sheets. Reducing costs and supply chain risk by multi-sourcing components can be beneficial as long as all the components have been tested and verified to meet your power model goals. Let's move on now and talk about battery life features in Windows. First up is the performance power slider. So the slider provides users with more control of finding that right balance between performance and power. Users can access this very easily from the top-level UI by clicking on the battery icon. And this feature was first introduced as an OEM opt-in feature in the Creators Update. In the latest version of Windows, it's enabled on all Intel and AMD devices that have a battery. The recommended slider position was renamed to Better Battery, and the default slider position, which is OEM configurable, is now Better Performance. So you may be wondering what happens when the user moves the slider from one position to another. What happens behind the scene? So there's two levers that are used by the slider to make trade-offs between better performance and more power, or more efficiency. So the first lever is the processor power management, or PPM tuning, which you're going to hear a lot about in the next 10-15 minutes. The second lever is power throttling of background applications on DC power. So before we dive into the details of each slider position and each lever, let's just go look at the power settings hierarchy that we've known for many years. All right, so at the bottom of the hierarchy, we have the traditional power schemes that you've seen before. So these define power, performance, and other functional settings, such as the timeout for disk or display. When the balance power scheme or any scheme that's derived from balance is selected, then the power scheme overlays take effect and the slider appears. PPM and energy performance preference values, EPP for short, that are defined in the overlays will override the settings that are defined in the power scheme level. So this is a hierarchy. Above overlays are scenario-specific profiles that engage during workloads such as full-screen video playback or real-time communications. These scenario profiles override all the settings defined in the two layers below. Settings that are not defined in the overlay level are inherited from the power scheme level. So the four slider positions are battery saver, better battery, better perf, and best performance. In addition to applying power-friendly PPM and EPP settings at the battery saver position, Windows enables the battery saver feature, which saves additional power by throttling background services and reducing screen brightness. So I actually used this slider many times, but most recently on my flight from Seattle to Taipei, I had two flights. So the first flight, I didn't have access to AC power, and I was trying to get some work done. So I moved the slider to the better battery position. And at some point, when I realized actually that there were going to be delays, I moved it to the battery saver position and reduced the screen brightness. On my second flight, I did have access to AC power, and I was actually working on some video editing. And so I wanted to see the results of that video editing job as soon as possible. I was really eager to see what it looked like. So I moved the slider over to the best performance position. So there's just a few examples of why a user would use this. So the first lever that I mentioned is PPM and EPP tuning, right? So PPM defines CPU settings such as the time it takes to ramp up a core to a higher frequency, or the number of cores to park when the system is idle. EPP tuning is available on Intel devices that have speed shift enabled and offers a simple way to define settings that either favor performance or power. The table on the right contains the current default EPP values for each slider position on AC and DC. So a couple things to keep in mind here. These values change from a release to release as we get feedback from you, and as well as our silicon partners. But these are the current values in Windows today. There's a note here, in the future release, we were planning on changing one of the values from, it looks like none to 70, EPP 70. With guidance from Intel, we recommend that you tune and override these defaults if you see a need to. So for example, if you're shipping a gaming device where you want to favor performance over power, you may not want to ship the inbox defaults. You may want to actually adjust the EPP settings to favor performance. So OEMs can customize their firmware with unique settings for each slider position. So I'll repeat that. In addition to all the PPM and EPP settings that we're going to be reviewing, you can also have your firmware respond differently or behave differently depending on which position the slider is in. And we actually have some more information in the Battery Life Lab coming up tomorrow. So if you're interested in learning more, we go through an example of a max fan speed. So in other words, we would maybe set the max fan speed to a certain level depending on which position the slider is in. So the second lever is power throttling. This is basically taking those background apps, anything that the user is not interacting with, and allowing them to get the same work done, but it's getting done at a slower rate, right? So this lever is only applicable to DC power, and it'll save about 11% in CPU power. It does this by scheduling threads of apps that are in the background on cores that are running at a lower, or that are set to a lower frequency. As you can see here in Task Manager, several Win32 and UWP apps are being power throttled while they're in the background. This lever is not OEM configurable, but it is user configurable. Power throttling is enabled on all 6th generation Intel chipsets, and AMD is working on adding support to the Ryzen mobile chipset in the future. Another new update to share on power throttling is that application developers can predefine the level of power throttling that their apps are subject to using the set process information function. So we have a link here to learn more. So basically, if you have something that you, for some reason, feel like this software should be opted out, or not necessarily opted out 100%, but maybe subject to power throttling at a less aggressive rate, this is something that you can use to tune your applications. So users have two options for opting out of power throttling. The first one is to opt specific apps out in the battery usage by app UI by unchecking the option here that says let Windows decide when this app can run in the background. Once you uncheck that, it shows you another checkbox called reduce the work the app can do when it's in the background. So if you uncheck those, now that app will no longer be power throttled. And we have a demo coming up in a few minutes to show you that. So as you can see here, I opted out Edge, and now Edge is disabled in Task Manager. Task Manager shows you that Edge is disabled. The second option is to opt out all apps by moving the slider position over to the best performance position. Notice how all the apps here are disabled. So that was a lot of information to digest. So let's just take a minute to summarize the chipset support for the slider as well as the two levers that we just talked about. So the slider user experience and generic PPM settings exist on all Intel and AMD devices. Processor-specific PPM settings can be applied to all chipsets. The perf EPP is only implemented on Intel 6th generation chipsets that have speed shift enabled. So Intel devices without speed shift and all AMD devices are configured with other processor-specific PPM settings. They're just not EPP, right? So power throttling is currently only available on the Intel 6th generation chipsets. Doesn't matter if it has speed shift or not. And AMD, as I mentioned, is actively working on adding support for power throttling. Key takeaway here is we encourage you to evaluate it, engage with your silicon vendor if you're interested in modifying any of the default values. And we're really, these are the values that we feel are right for kind of the majority of devices, but we do understand that you might want to use some custom settings. Using Windows provisioning, you're welcome to apply custom settings. Now I'd like to take an opportunity to congratulate everyone in the room, especially those folks in the last 5 rows. You passed today's eye exam. This is kind of a big eye chart, so congratulations. Big round of applause for you. All right, so with that, I'm going to head over to the podium here and walk you through some slider demos. All right, great. We're all set up. Okay, so the first demo we're going to walk through is looking up the PPM settings using WPR, which we're going to get into more later. It's Windows Performance Recorder, and WPA, the Windows Performance Analyzer. So the first step is to start WPR logging. It's as simple as running a command line here. We're going to stop WPR logging because that's enough tracing to get the events that we need. So I type in WPR-stop ppm.etl. Step 3, we're going to load ppm etl and WPA by typing WPA space ppm.etl. So once WPA loads, we're going to click on Trace, System Configuration, and Power Settings, and then we'll zoom into the various power settings. I'd love to spend the next couple hours walking through each of these with you, but I'm just going to show you them and then direct you to some MSDN documentation if you want to learn more about them. So we'll go to Trace, System Configuration. Let's move this out of the way. And we're going to click on Power Settings here. So as I mentioned in the intro slide, some of the settings are functional settings, right? Like the screen timeout, and other settings are like processor, tuning settings. So this is a long list of over 50 different settings. As I mentioned, some of them are like, how long does it take before a core will be parked? What are the minimum number of cores that should be parked, right? So these are all documented, or most of them are documented on MSDN, and we have links inside the slide deck, which will be shared after the event. All right, let's switch to the next part of our demo. Okay, so do you remember the hierarchy that we went over? So there's the power schemes, and then on top of that was the overlays. So what we're doing right now is we want to look up the overlays that have been defined on my machine. So to do that, we are going to use a tool called PowerCFG, and we're going to run this long command here, which is going to pipe the output to a text file, and then we'll take a look at what's in that text file. All right, so the key takeaways here are this is the name of the overlay that we queried. It's scheme min. This corresponds to the better battery life overlay. The setting that's defined on this machine is perf EPP, and then here we have the values for AC and DC power settings. So all you have to do is convert this from hex to decimal, and then you get to see what this value is. I believe this is 70. All right, so now let's look up better performance overlay. And we get, this is derived from the balanced scheme, but we get slightly different values. So it looks like this value might be the same as it was in the previous overlay. But now on AC, we have a unique value for that. And let's move on to the max performance. And in this one, there's a lot more settings here. So as I mentioned in the slide deck, there's a link that you can learn more about most of these PPM settings. Yes, so this link that the script is trying to go to is available in the slide deck, so you can learn more once the slides are posted. Let me bring up the last demo here. Okay, so we just talked about PPM settings that are inbox, EPP settings that are inbox. So we talked about overlays, which will override the inbox settings. Now we're going to switch gears and talk about power throttling. So what I'm going to do is I'm going to launch Task Manager, because that's a quick, easy way to figure out if power throttling is engaged or not. So I'm going to click on the Details tab, and once I'm in there, I'm going to right-click on the columns, and then hit Select Columns. And I'm going to scroll all the way down to the bottom until I find power throttling. So I'm going to click that, hit OK, and then now I'm going to have to drag that over here. There we go. Let's get out of Zoom. There we go. Okay. Almost there. Perfect. All right, so first observation here is, well, every single app or every single process right now is being power throttled. Why is that? Well, I haven't disconnected from AC power yet, so power throttling only applies to DC power. So if I pull the power cord out, we should start to see in a minute or so several applications. Oops, bring that back up. Details. There we go. And you can see a couple calculator and a couple other applications are now being power throttled. There are some applications that are exempt, like audio DG. If you're playing back music, that process will be exempt. All right. So the second option for users to essentially control power throttling is to use the battery usage by app. So I'm going to type in battery saver. I'm going to click on this link here called battery usage by app. And bear with me, right? Yep, there it is. Okay, Edge is already open. Perfect. So I'm going to go here and uncheck this, which brings up this menu option. So reduce the work the app can do when it's in the background. So I've unchecked that. So that should opt me out. So if I go back to Task Manager, let's go find Microsoft Edge. There we go. So Microsoft Edge is completely disabled now. The user is opted out of being power throttled. So let's go to the the next option, which is simply to opt out all apps. So we see a few apps here that are being power throttled. So let's go ahead and click on the battery icon and then move the slider to the best performance position. All right, so once I do that, every single app has been opted out of power throttling. Perfect. All right, so let's get out of here. Set up for the next. Perfect. All right, so we're going to switch back to the slides now. Thank you. All right, so let's talk about the battery saver and battery usage by app experience. The battery saver user experience extends battery life by limiting background activity and reducing the screen brightness by 30%. By default, this feature will engage when the battery life reaches 20%. This is user configurable. Clicking on the battery usage by app brings up a stack-ranked list of applications that impact your battery life. As you can see from the screenshot, Outlook, Edge, PowerPoint, and OneDrive were the top 4 consumers of energy on my device over the last 24 hours. And the battery life you see here, the battery life data you see here was provided by the Energy Estimation Engine service, which leads us to the next battery life related topic that I wanted to share with you today. So can I get a quick show of hands? How many folks in the room have heard about E3 or have heard us? Okay, good. So there are a few hands, about half the hands didn't go up, so I will spend a minute just to kind of cover. This is a service that's running in-box on all Windows 10 devices that have a battery. Its job is to really break down the energy consumption of apps and services and hardware. Devices that don't have dedicated power meters will basically fall back to the default software estimation code path, which estimates energy consumption. The software estimation accuracy of CPU power model on recent Intel chipsets is about 89% accurate. Software estimation for the other power models like display, network, disk is less than 70%. And I say less than because it just depends on how different that device is that you're testing how different the power characteristics are from the machine we use to generate our default E3 profiles in the OS. So as you can see in this table, the accuracy of the hardware-based measurements on all 4 power models is essentially greater than 98%. So with that in mind, Microsoft highly recommends utilizing hardware power meters on pre-production devices as they are low cost and it helps you scale out the energy optimization efforts within your organization. So we'll review the other power meter options in more detail in a few minutes. So Microsoft continues to invest in E3 by improving the accuracy of power models, including the display power model. There's been an increase in OEM interest as far as including power meter chips on pre-production devices. So with that in mind, we're working to improve the enablement documentation in this area. Microsoft leverages the E3 telemetry on a daily basis to track both improvements and regressions in OS components. So if Search Indexer or Cortana or another inbox component either gets better or regresses from a power perspective, our feature teams are aware of it. We use E3 to track using Windows Insider's builds. We're continuing to learn how to interpret and analyze the E3 telemetry, and we're adding new filtering capabilities every day. So let's move on to the next Windows power-saving feature called software-defined batteries, call it SDB for short. This is a feature in Windows that applies to devices that have 2 or more batteries. The SDB implementation in Fall Creators Update provides a standard battery management interface for autonomous and non-autonomous charging tasks. SDB also offers a simple solution for age balancing batteries. As you can see from the table on the right, without SDB, the internal battery ages at a faster rate than the detachable battery, reducing battery life in the long run. We're considering expanding the value proposition of SDB by adding new scenarios in future versions of Windows. I invite you to review the recently published SDB API documentation that's available today on Microsoft Docs. The last Windows power savings feature that we're covering today is low power media playback. So media scenarios such as full screen video playback can be optimized by including audio offload capable audio devices and panels that support low refresh rate. Offloading audio, as I mentioned, saves between 4 and 14% power, and low refresh rate panels can reduce power consumption by 3 to 5%. So if you have a device that already supports audio offload, we've been hearing reports of some bugs in the audio IHV ecosystem. A lot of those bugs have been fixed, so we encourage you just to reach out to your audio IHV and get the latest version of that driver and apply it to your image. We recommend that reviewers and end users use UWP apps, especially these are essentially taking advantage of power-saving features that Win32 media playback apps do not take advantage of. The Battery Life Lab that we have coming up tomorrow contains several exercises that walk through the steps of verifying power-saving features are engaged during media playback. Let's switch gears and talk about battery life assessments. So the assessment toolkit is a component of the ADK, the Assessment and Deployment Kit. This toolkit contains automated performance and quality assessments and energy efficiency workloads that enable partners to optimize Windows devices during device bring-up. Perf assessments generate metrics such as memory footprint, app launch time, boot time, shutdown, etc. Energy efficiency workloads generate battery life rundown stats. All the assessments and workloads have options to create verbose and ETW logs, which can be used in tools like WPA or MXA to do some rich analysis and improve the experience and squeeze out more battery life. Assessments and workloads can run directly from the Windows Assessment Console, or you can package them up onto a USB stick, put it onto a test machine, and run it on another device. In the Fall Creators Update, we added new energy efficiency workloads, including office productivity and video playback. All assessments and workloads are supported on x86, AMD 64, and Windows on Snapdragon. So I encourage you and your team to give these new assessments a test drive. You can download them and install the Windows Assessment Toolkit from the RTM drop or from the preview location. If you go to the preview location, you will need your EAP or Windows Insider's program login information. If you're interested in checking out the latest assessment toolkit and analysis tools, the screenshot on the right highlights the 3 components that you need to install in order to use all these tools that we're talking about. So here's just a quick look at the energy efficiency workloads that we have today. In addition to the assessments we discussed in previous slides, there's an energy efficiency workload for system idle and modern standby. If you're new to assessments, we recommend you start out using the full screen media playback or idle energy efficiency workload, because those are pretty straightforward and it gives you quick information and logs back. Once the energy efficiency job is run on a test machine, you can load and view the results in Windows Assessment Console. The screenshot on the left contains the high-level energy metrics, such as projected time to shutdown. If you navigate to the results folder in Explorer, you'll have steady state, startup ETL, as well as some E3 logs. So I'm going to head back to the demo machine and walk through some ADK and E3 log demos. Okay, so the first one is we're going to launch the Windows Assessment Console. And I'm just going to kind of walk through the process you would take to create a new job. So let's go ahead and zoom in. I'm going to click on Options, New Job, Create an Energy Efficiency Job. And we can add, a job could contain multiple assessments. So for now, we'll just add one assessment. So I'm going to click on Add Assessments. I'm going to scroll down to the new Windows 10 full screen media playback workload. Once I click on that, we can adjust some of the parameters to the assessment by unchecking this box here. So yeah, I'd like a startup trace, steady state trace. These are actionable traces that you don't get from other tool sets out there that do battery rundown. So down here in the execution parameters, playback source, we can do custom local. So if you have your own favorite clip that you guys use internally, you can choose a custom path and just use your own content. You can also use the default soccer clip, which I'm sure many of you who are familiar with these assessments dislike greatly, as much as I do. The default auto select will basically choose between 720p and 1080p based on the native resolution of the screen. We have a movies and TV app streaming content of a Halo 2 clip and a Netflix workload. So at this point, I would either click on package and then just create a package that I would put on a USB stick and run it on a test machine, or I could just run it on this machine right now. So I'm going to go ahead and load up some results. Ran this assessment on my machine last weekend. And there's a lot of general energy efficiency metrics. I'm not going to spend time on each of these. I just kind of wanted to give you a high-level overview, especially for the folks in the room who haven't used the assessment console before. But you have projected time to shutdown. This is 725 minutes, and it's based on draining the battery from 100% down to 48%. So we typically recommend running these assessments for at least a 20% rundown just to get a decent average for the drain rate. So in addition to getting these high-level metrics, we also have the E3 log as well as ETL files. So I will go ahead and navigate to the results here. And we can see here, we've got the E3 log in both CSV and XML format. We've got the 2 ETL files. ETL files can be fairly large. These are, looks like 557 meg, 216 meg. So typically the next kind of step in the process here would be to load these up in tools like WPA and MXA, which we'll talk about more in a few minutes. So I'm going to go ahead and just show you what we can do with E3 data. We have a training video on Channel 9 that goes into more depth here. It describes some of the columns here, and also the lab document that we have for tomorrow's battery life lab goes into details for each of these columns, so I recommend you check that out. So we don't have time to go into that right now, so what I'm going to do is just go ahead and create a pivot table and show you kind of what E3 data looks like in a summarized manner. So I'm going to select all the data, hit Create Pivot Table. Let's bring the app over and look at CPU energy consumption. Where'd you go? There we go. So I'll zoom in just a second here. So I'm going to go ahead and sort by CPU energy, large to small. Bring this over here, and what we see at the top is the media player, the UWP media app. These values here are in millijoules, so this is raw energy data. And you can see here that the #1 app that consumed CPU energy was the media app. Now, so what we've seen sometimes when doing test passes on pre-production devices is we'll run these workloads where we expect to see something like this, but we actually see in the top 5 or 10 components that consumed energy an application that's running in the background that's not adding any value to the user as they're watching a movie on a plane, right? You can do other things like we can create a pivot chart. Where'd you go? There we go, pivot chart. Before we do that, let me add in display, disk, and network. And then let me filter out app ID. Okay, let's create the chart first, then we'll filter. So I'm going to go ahead and choose the 3D stacked chart, and let's remove all except for the video app. Okay, so I'll zoom in. So basically what we see here is the sum of display energy is, over 95% of the energy went to the display, basically, right? This scenario from a CPU perspective is highly optimized. As I mentioned in that earlier slide where we showed the different hierarchy of all the PPM settings, video playback has a scenario profile that takes effect when you're in full screen playback, and so it optimizes CPU energy consumption. You're doing lots of offload with the GPU. And so, as you can see here, this is a local playback workload that I had run, so there's really hardly any network. And the disk energy consumption is fairly low as well because we take a 5-minute clip and loop it, so it's in the cache. All right, so let me just get set up for the next demo, and then we'll switch back to the slides. All right, let's move on to hardware power measurement solutions that our IHV partners have been actively working on. This table compares several power instrumented solutions that are available to partners for debugging and optimizing for power. Fully instrumented devices typically monitor 32 to 64, I've seen as high as actually 96 rails. They have low component flexibility. They're not compatible with E3, and they do not scale due to their high cost. The Intel Power Instrumented HDK falls in between the fully instrumented devices and low-cost individual power meters. The HDK has high component flexibility, it's compatible with E3, has medium scale, and can monitor 36 rails. Individual power meter chips are low cost, they're compatible with E3, and they have high scale and can monitor 4 rails each. So let's dig a little deeper into each of these power monitoring solutions. Maxim developed the Max 34407 power meter when E3 was first introduced in the original version of Windows 10. The chip was used in several pre-production and production devices, and Maxim is currently working on a new release called the Max 34417, which is due out sometime in early 2018. I encourage you to reach out directly to Maxim at analog@maximintegrated.com if you have any follow-up questions. Microchip released the PAC 1934 power meter this past fall. This power meter is in full production. QFN samples are available for development, and their driver and energy utilities are available for download on the web. You can learn more about their part on their press release and product page. And it's worth mentioning that 9 of the power meter chips, of these power meter chips, are included in the HDK from Intel. If you want to learn more, please reach out directly to Microchip at e3@microchip.com. I'm sure they'll be happy to chat with you. So as you heard from Jackie Zhao earlier, Intel partnered with Microsoft and Microchip to develop a precise power measurement solution that is expected to cost less than $1,000 and is capable of monitoring power on 36 rails. Intel is developing the hardware design, BIOS, EC, and samples. Microsoft developed the power meter driver and the application that's used for viewing and saving the power data. And as I mentioned earlier, Microchip is delivering the power meters. This solution enables OEMs and ODMs to plug and play different components and firmware to measure power and select parts for your BOM that meet your power modeling goals. The HDK supports measuring power from a remote PC, so this is an ideal setup for optimizing modern standby devices, right? So you put the device you put all your components, plug them into this HDK, you put the machine in standby, and now you see from a remote machine all 36 rails what they're consuming, and you can do some pretty rich debugging with that. So I'm going to switch over to a short HDK demo video that walks through the HDK's capabilities.
大家好，我是来自微软中国的工程师胡代乾。现在我向大家演示一下 HDK 以及它所具有的功耗量测功能。现在大家看到的就是我们的 HDK 平台，上面有一个小一点的板子，这个就是 Core Board， 有 SOC 内存以及和 SOC 相关的一些 Component。下面这块大一点的板子是 I/O Board， 会有很多的硬件接口，这些硬件接口可以很方便的插入外设，比如 eMMC、WiFi、显卡、Sensor 和 Touch。现在我们来演示一下如何测量一块 SATA 硬盘的实时功耗情况。首先，我们需要把一块 SATA 硬盘连接到我们的 HDK 上。在使用 HDK 功耗量测之前，我们先来看看传统的功耗量测设备是如何测量的。这就是我们的硬件功耗量测设备，大家可以看到相当的复杂，体积也比较的大，几乎和我们的 HDK I/O Board 差不多大。要量测 SATA 硬盘的功耗情况，首先我们需要从 SATA 硬盘飞线到功耗量测设备上，然后需要用到硬件测量设备配套的软件进行实时功耗的数据采集。这个软件的学习曲线非常的高，需要非常专业的人员才能够熟练的操作并进行数据的采集。现在我们来看看如何用 HDK 量测硬盘的实时功耗情况。首先，硬件的连接非常的简单，只需要一根 USB 线从 HDK 连接到另外一台 PC 上，然后在 PC 上面装上硬件驱动，就可以用量测软件进行功耗的实时量测了。这就是功耗量测工具，左边可以勾选所有量测的线路。现在我们需要量测 SATA 硬盘，在这里勾选 SATA 硬盘的线路，那么采集到的数据就已经出来了。可以看到数据比较平缓。接下来我们拷贝个文件到 SATA 硬盘，看一下实时功耗的变化情况。可以看到功耗一下子就上升到了25000毫瓦左右。通过上面的演示，可以非常清楚地看到，用 HDK 的功耗量测方案相比于传统的。
So if you want to get a closer look at this HDK, please check out the HDK booth here at WinHEC. Let's switch gears now and talk about optimization and analysis tools. We'll start with the inbox utility called PowerCFG. PowerCFG is used for setting, querying, and diagnosing power-related settings and issues. This slide contains a list of common usages, including System Power Report, ShrumUtil, which is the E3 log, energy reports, battery reports, and an option to look up to see which sleep states your system supports. In addition to the resources listed here, there are several exercises in the Battery Life Lab that we'll walk through tomorrow regarding all these different Power CFG commands and how to look at the logs that they generate. System Power Report generates power stats during modern standby and active user sessions. I just want to make sure that everybody's aware. You might be wondering why this System Power Report looks very familiar if you've had modern standby systems and run sleep study reports before. It looks very similar. So I just want to emphasize that System Power Report applies to both active user sessions as well as modern standby sessions. To collect a System Power Report, you launch an elevated command prompt and type in powercfg/SPR. This report contains E3 energy data for each active and modern standby session. For modern standby sessions, SPR lists the top offenders that activate and prevent the device from either remaining or entering DRIPS. DRIPS is the deepest runtime idle platform state. It's essentially the low power floor for a modern standby machine. For active user sessions, SPR lists the various screen brightness levels used and provides E3 data broken down by application and E3 power model. So I'm going to go ahead and walk you through a few more demos here. We're going to look at the active full screen video playback session in SPR, and then we're going to look at a modern standby session in SPR. All right, so let's run this demo script. So the first thing we're going to do is look at a full screen video playback session in a System Power Report. Okay, so what you see at the top of the System Power Report is some power state transitions. So you can see I drained the battery from 100% down to about 20% on the 21st of November. We can filter out sessions. So if you know you're focusing on an active session that's greater than 10 minutes, we can click here, and there is the session that we just saw in the chart above, 80% drain. So I'm going to click on that. That brings us to the details for that session. So what I learned from the first part here is that the screen brightness throughout this several hours of using my machine varied from fairly low to about, looks like 30, 45, 50%. Scrolling down to the SRUM data, the data that we had just looked at in Excel, right, using those E3 logs, that was E3 data that was generated for a specific ADK workload. This data is coming from sessions that were logged in this SPR report. So if I click on this, it looks like I was using Edge to stream video. And you can see a breakdown here. So the CPU, very consistent to what we saw with the ADK results, right? The E3 log that was generated there. CPU energy was very efficient. Most of the energy went to the display. In this particular example, I did run a tool in the background that's supposed to represent kind of one of those applications that's not adding value to the user. So this RWS stands for real world stress. It's just an internal tool that we use for applying stress to the system for various test purposes. And so in this case, you can see it consumed 370 milliwatts. And it's not something we would expect to see if the user is simply browsing the web or streaming YouTube. So let's go ahead and move on here. So step 2, we're going to open up System Power Report that was generated on 2 different modern standby sessions. So let me go ahead and filter. So we'll look at standby sessions that were longer than 10 minutes, and it looks like there's 2 of them. And so, you know, these were pretty short sessions because I was just generating these logs for today's demo. But the key difference is that the first one had 98% software drips, and the second one had 0% software drips. So let's click on the first one. And you can see the top offenders here. These are basically components that are keeping the machine from entering or remaining in drips. Everything's green for a reason. Everything was behaving fairly well. There was the Microsoft component, Universal Telemetry Client, that was running for 2% of the time. But this is fairly clean session. So if we scroll back up to the top, let's go ahead and click on that second session, which had 0% software drips. So I'm going to click here. And what we see is the number one offender here, it's a USB compliant host controller. It was active 99% of the time. And so in order to generate these logs for this demo to share with you today, what I did was I simply went into Device Manager and I went to the USB hub, and there's an option that says basically whether or not you want to allow the device to go to sleep. So let's go ahead and zoom out here. So this is basically the case. Allow the computer to turn off this device to save power. So when it was checked, we had the 98% software and hardware drips. When it was unchecked, we had the 0% software and hardware drips. All right, so I'm going to switch back to the slides now. So let's talk about Windows Performance Recorder, WPR. The energy efficiency workloads are very helpful when you want to capture an ETW log during an automated scenario, but sometimes you want a manually collected log because you notice a problem during, say, a scenario or workload where you don't have an automated test to use. So this is where WPR comes in handy. You can use this tool to generate a log. There's a command line version that's available in box in Windows, and there's also a UI version that ships with the ADK. WPA is a very powerful ETW analysis tool that can be used to triage and diagnose both performance and energy efficiency issues. This tool is available in the ADK, and you'll hear a lot more about WPA tomorrow during Sylvain's performance session. In this talk, we'll briefly review a new view that was providing insights into what the system timer resolution looks like and which apps are trying to lower the system timer resolution. System timer resolution is expected to be at 15.6 milliseconds or higher when the device is on battery and the system is idle. Of course, there are scenarios like real-time communications or any time-critical applications that may lower the system timer resolution. That'll help reduce latency, but it all comes at a cost. So lowering the system timer resolution can increase power consumption by more than 100 milliwatts. So it's important to be very judicious and careful about which applications you're including on your OEM image. In the Fall Creators Update, we have a way for you to easily view which applications in your image preload are responsible for lowering the system timer resolution. So last but not least, let's review the Media Experience Analyzer tool, also known as MXA. Similar to WPA, MXA is an ETW analysis tool that offers unique views designed for optimizing media scenarios for quality and for power. As you'll see from the Battery Life Lab exercises, this tool has views that enable you to verify the key power-saving features are enabled. It also has the ability to load and align multiple traces in the same timeline and correlate power data that's generated by like a HDK type kit with system activity. This tool also ships with the ADK. Demo time. All right, we're going to switch to back to the demo machine, and this is our last demo. Perfect. Everybody can see. Awesome. Okay, so what we're going to do is we're going to unplug from AC power and collect an ETW log while WPR is changing the system. We're going to collect an ETW log and then using WPR, and then we're going to use a utility that we have to change the system time resolution. We'll take that ETW log and look at it in WPA. So let's get started. I've already unplugged the device. I'm going to hit continue. This is the command to start logging. So I'm going to run WPR -start power file mode. All right, so step 3 is to run this utility that will set the system timer resolution to 3 different values for 3 seconds at a time. So half a millisecond, 1 millisecond, and 4 milliseconds. So hit enter. It's reducing my battery life as we speak. There we go. All right, so let's stop WPR logging. And we're going to load this trace in WPA. So to access the system timer resolution view, we're going to expand the power node and scroll down to the timer resolution node. So I'm actually going to double click on this, and then I'm going to X out here to give us some more real estate. So everyone can see that? Perfect. All right, so the resolution here is 500 milliseconds. It tells you which process was responsible for lowering the timer resolution. You can measure to see how long it was lowered for. So as I mentioned, the tool is designed to run it for about 3 seconds. So basically, the x-axis here is time. The y-axis is the timer resolution. The interesting thing here is that not only can you see all 3 instances where it went from half a millisecond to 1 millisecond to 4 milliseconds, but the tool that I really enjoy using for demos like this, called Zoom It, also lowers the timer resolution the entire time to 1 millisecond. Okay, so the last demo I wanted to share with you is using MXA. MXA has a fairly high learning curve, and so we do have some Channel 9 videos that I encourage you to check out on the Defrag Tools series. But for now, just bear with me. I'm going to quickly run through the process of looking at a trace in MXA. So I'm going to launch MXA, Media Experience Analyzer, open a file. Let's put this in our path. Perfect. There it is. All right, turn off symbol lookup. Okay, so let me set some context around this trace that we're looking at. It was captured during full screen video playback, and this was taken on a machine that supports that feature I had mentioned a few times earlier in the talk, where we'll reduce the refresh rate of the panel. So we go from 60 hertz down to 48 hertz when we're playing back 24 frames per second content in full screen mode, okay? So kind of looks like lots of different colors and art here. What we're going to do is we're just going to focus on one data set over here. All these different data sets are broken down by CPU, disk, GPU, etc. There's one here on the left called DX, VSync, ISR, and DPC cadence. So I'm going to go ahead and drag this over to a panel here, and then I'm going to zoom in down here. So what we're looking at is the x-axis is time, just like we saw in WPA. The y-axis is actually the delta between VSyncs. So every time your screen refreshes 60 times a second, it basically generates this graph based on that delta between how fast your screen is refreshing. So basically down here, we were at a nice 16.6 milliseconds, which is 60 hertz. When it jumps here, this is essentially once the machine, let's see, about 15, 17 seconds after the playback started, it jumped to 48 hertz. And so we're not going into any long training here on MXA. I just wanted to kind of give you, especially the folks in the room who haven't used some of these analysis tools before, I wanted to give you a quick preview of what these tools do. And I definitely encourage you to check out the Battery Life Lab tomorrow. So switch back real quick to our final slide. So that wraps up our Optimizing Windows Devices for Battery Life session. I hope this talk inspired you to learn more about battery life features in Windows, battery life assessments, power measurement solutions, and optimization and analysis tools. Thank you very much for your time this afternoon, and enjoy the rest of WinHEC. Thank you.